In this video, we introduce alternating currents and we investigate the power dissipated by a resistor with alternating current passing through it. Along the way, we develop formulas for the RMS or root mean square values of current, voltage, and power. And finally, we wrap things up with a few simple examples of resistor calculations involving alternating current. So in the top left of the screen here, I have kind of a schematic view of what's going on inside of a resistor that experiences a direct current voltage that's indicated by the little dashes over the top of the V, like you might see on a multimeter. And in this case, the voltage never changes. The left side is always the high voltage side, and the electrons will always drift from that low potential on the right to the high potential on the left at an average speed called the drift velocity. In contrast, in the second picture, I have an alternating voltage. So the right-hand side will remain the ground side, but my voltage is now changing sinusoidally. It's given by a sine function. And this voltage has some peak value V naught, and it's going to oscillate between positive V naught and negative V naught, which means the direction of the potential difference is periodically switching across this resistor. And as a result, the electrons are just jiggling back and forth rapidly instead of drifting over long distances in one direction. Now this resistor will still dissipate power as heat because these electrons are still colliding with atoms in the material. It's just that they're wiggling really fast instead of drifting slowly in one direction. Now I wanted to throw in a couple reminders about sinusoidal functions over here on the left, and then we'll get into the example on the right. This little coefficient of t, that's omega, that determines the period of the oscillations of this function. And period is given by 2 pi over the coefficient of t, or 2 pi over omega. If I then solve for omega, this means omega is 2 pi over t, where t is the period. And then if I remember that 1 over the period is the frequency, I find that omega is 2 pi times the frequency. So we have these sort of 3 different equivalent ways of describing how rapidly this function oscillates. We have the period, capital T, the frequency, that's the reciprocal of the period, and it would be measured in hertz. And then omega is called the angular frequency. Let's take a look at our example real quick. So in the United States, houses are wired with an AC voltage such that the peak voltage is 156 volts. The average voltage, which is also called the RMS voltage, is typically around 110 to 120, so I'm just putting 110 here. And I'll talk about how that's computed from the peak voltage a bit later in this video. And then the frequency of this oscillating voltage is 60 hertz or 60 oscillations per second. In part A, I'm asked for the period of oscillation, so that's just 1 over f. That's 1/60th of a second. So we get a full wiggle of this sinusoidal voltage every 1/60th of a second. And then we're asked for the angular frequency, and so I could say omega is 2 pi f. And this gives me 377, just keeping 3 sig figs. And then I have to think about what the units of omega are. So in the argument of the sine function, I've got to have radians, and the t is carrying units of seconds, so that means omega must be radians per second. Radians are technically unitless, so we would officially have to express this as like 377 inverse seconds or 377 per seconds. I don't think there's any problem with keeping the radians there though, just to remind yourself. Finally, we're supposed to plot V of t and label the amplitude and the period of the oscillations. And of course, I already did the plot. This is just our basic sine function, but I wanted to label the period on here. So that horizontal axis is t, the vertical axis is V of t. The period is the time for one complete wiggle, so that covers this amount of horizontal distance on the graph. And then the amplitude here is the distance between the midline and the peak, or midline and trough. And we already have a name for this. The amplitude is the peak voltage V naught. And we have a number for this in this particular example. That's 156 volts positive. And then on the other end of things, we get 156 volts negative. In other words, a potential difference in the opposite direction. So when we apply an alternating voltage over a resistor, the current still obeys Ohm's law. So I could write down I equals V over R. And that current response through the resistor, it's always in phase with the voltage across the resistor. So when I have the peak voltage applied to the resistor, that's the same moment in time that I get the peak current. So in this picture, the graphs of voltage as a function of time and current as a function of time, they look identical, but they have different units on the vertical axis. In my first picture, it'd be volts. In my second picture, it would be amps. And notice that I indicated in the current formula that the peak current could be written as the peak voltage divided by the resistance. Again, just applying Ohm's law. And I want to point out here real quick that the voltage for every wiggle of the sine function is going to hit 0 twice. And so the current hits 0 twice for every wiggle of the sine function. Now the power dissipated by the resistor is still given by the old formula IV. But now I and V are both functions of time given by this first formula and second formula above. So I get I naught times V naught, so the product of the peak current and the peak voltage, times the square of sine omega t. And the graph looks like this. And notice that I just found out the current flowing through the resistor is 0 twice for every period. And so the power is as well. This means that for a 60 hertz alternating voltage, the power hits 0 120 times per second. Now the peak power is the high point of this graph here, and that's just given by I naught V naught. So I can write down a useful formula from this. I can call it P naught equals I naught V naught. And I have a formula for the peak power in terms of the peak current and the peak voltage across the resistor. Now we're occasionally interested in the peak power, but the thing that has by far the most practical application is the average power dissipated by a resistor. That's what's going to determine, for example, how much heat and light is produced by a filament in a light bulb. It's the average energy output. So for those of you with a little bit of calculus background, you might want to follow this derivation. It doesn't take that much time. If you want to skip it, go down to the description and you can click through the chapters to skip over the calculus. So what I'm trying to do here is compute the average value of power. So here's the graph of the power as a function of time. And the way I get the average value of a function is I integrate over some interval. And what I'm doing here is actually just one period of the sinusoidal function. So 0 to t, and then you divide by the width of that interval. To justify why we do this real quick, let's just turn it around. I have average power times t equals the integral from 0 to t, in other words, the area under this function. Well, what's the area under a power function? Power gives you the time rate of energy dissipated. So when I find the area under this, I get the energy. So if I take my average power in watts, that's joules per second, and then multiply by the time that's been applied for, I get the total energy. In other words, what I'm doing is modeling this total energy captured in the area as if it's coming from a constant function, in other words, a horizontal line. And I just say, well, what constant value multiplied by time would give me the correct amount of energy? That it makes a lot of sense to call this the average. So the calculus part is that we need to actually perform this integral. And my power as a function of time is given by I naught V naught sine squared omega t. But remember that omega could be written as 2 pi divided by the period. While I do that, I'm going to go ahead and pull the constants I naught and V naught out of here. So I've basically just got to integrate the square of the sine function. There's a constant out in front that would ordinarily interact with the chain rule, but I'm going to come up with an argument that allows us to circumvent that issue anyway. Oops, forgot a capital T down there. Okay. So the standard way to handle the integral of the square of the sine function is to use an identity. Sine squared is 1/2 times the quantity 1 minus cosine of twice the angle. I'm going to leave the 1/2 out in front. And I get 1 minus cosine of twice the angle, so cosine of 4 pi over capital T times little t. And you could guess the antiderivative of the cosine of 4 pi over t times t, and that's fine. But I see a trick that could save us some time here. This cosine function is experiencing an integer number of periods on the integration interval. To justify that real quick, the period of that cosine function is 2 pi divided by the coefficient of little t. So that's 2 pi divided by 4 pi over t. Pi's cancel. And I end up with 1/2 times the period of the original sine function. So when I integrate from 0 to t, this cosine piece experiences 2 whole periods. Well, a simple sine or cosine experiencing an integer number of periods spends exactly as much time above the t-axis as it does below, so I'm guaranteed to have this piece vanish when I integrate. Go ahead and check against that by guessing the antiderivative. That would be the sine of 4 pi over capital T times little t multiplied by big T over 4 pi. When you evaluate that across the endpoints, you're going to get 0. So that piece is done. And out in front, I have I naught V naught over capital T. And there's a 1/2 tagging along. The antiderivative of 1 is just little t. You evaluate from 0 to big T. The lower limit vanishes, and I get a capital T out of this. Capital T's cancel, and I find out that my average power output is 1/2 I naught V naught. So certainly we want that formula for the average power. I can call it P bar, but it can also be called P RMS. And we'll get into where that notation comes from in just a moment. And that's 1/2 I naught V naught. So you multiply the peak current and the peak voltage and you divide by 2, you've got your average power. One more thing I'd like to point out before we move to the next slide is that the value of this integral turned out to be 1/2 t. And it's not the last time we're going to use it in this video, so let's just make a mental note of that. When I integrate the square of sine omega t over 1 period, I end up with 1/2 times t. Next, our goal in this slide is to relate the average power to the average value of the voltage and the average value of the current through a resistor. But what I'm pointing out in my first picture here is a problem with the idea of the average value of the voltage. If I were to directly attempt to compute the average value of the voltage, I would integrate over 1 period and then divide by the length of that period. And then what I've shaded in here is the fact that I have exactly the same amount of area above the t-axis as I do below. Again, if I integrate a sinusoidal function over an integer number of periods, the result always vanishes. Okay, this is upsetting. My average voltage is going to be 0. If I do the same thing with the current, I would get 0 because it's always in phase with the voltage. The graph is basically the same. So we've got to do something to define a meaningful average for the voltage and the current. And the trick here is to just go ahead and square this thing. And I end up with this graph. And then what I'll do is get the average value of the square of the voltage, and then I'll square root the result. So I'm square rooting an average value of the square of the voltage. This is where the phrase root mean squared comes from. I'm going to take the square root of the mean of the square of the voltage. Okay, so we've given up on the idea of taking a direct average. We're going to square the voltage function. We're going to take the average by computing an integral, and then we're going to square root the result and see what happens. So let's get into this integral. Again, I'm computing the mean of the square right now, and then I'm going to make up for that by square rooting later on. And my voltage as a function of time is V naught sine omega t, so I'm going to get V naught squared sine squared omega t dt. I can pull the V naught squared out in front of that. It's V naught over t, integral from 0 to t, sine squared omega t dt. You could relate this omega to the period if you like. It's 2 pi divided by the period. And again, you would have to use the trig identity to integrate this thing, but this is the same exact integral that we just did, and we found out that it's equal to 1/2 t. So I get V naught squared over t times 1/2 t. The t's cancel, and I end up with 1/2 V naught squared. Now to wrap things up, our new definition of average for the voltage, again it's called RMS, is going to be the square root of the average of the square of that function. So the square root of this thing, that gives me a 1 over root 2 times the peak voltage V naught. And now I have a nice formula for computing the RMS value of a voltage from the peak value. Notice that I could do exactly the same thing for the current as a function of time. And the only thing that changes is the constant out in front. It'll be I naught squared instead of a V naught squared. So my RMS value of current is also 1 over root 2 times the peak value of current. Finally, we had just discovered that the average value of power, or the RMS power, is given by 1/2 I naught V naught, but I could rewrite this as 1 over root 2 I naught times 1 over root 2 V naught, and then I discover the average value of power is really just the product of my RMS current and my RMS voltage. So these RMS definitions, they get us back to the original definition of power as I times V. It's just in an average sense now. Notice that this power formula can be reworked by using Ohm's law. I can say that I is V over R, I RMS is V RMS over R, and I end up with V RMS squared over R. Alternatively, I could rework the original power formula here by replacing V with IR, or I RMS times the resistance, and I get I RMS squared times R. So those can also be useful. All right, so the main takeaway here, I think, is to just remember that RMS is a type of average current output and average voltage output. And the way we defined that average, it made it so our old power formula was still valid, so you don't have to remember some new and exotic power formula. So let's wrap things up with a summary of key formulas and a few simple examples. First in my list is just the voltage as a function of time for AC voltage. Then current as a function of time through a resistor that's experiencing an AC voltage, and this is in phase with the voltage. In other words, they have the exact same trig function. Then I relate that coefficient of little t to the period and the frequency of oscillations for the voltage with these standard formulas. Next, the way we compute the average voltage is with this RMS idea that involves using a little bit of calculus to take an average. And it turns out to be 1 over root 2 times the peak voltage, and similar for RMS currents. Peak power was just I times V, which can be reworked with Ohm's law into these two other forms. No surprises there. Average power turned out, again, using a little bit of calculus, to be 1/2 times the product of the peak current and voltage. But plugging in the definitions of RMS current and voltage, I retrieve my old power formula. The average power output is going to be the product of the RMS current and voltage. And finally, using Ohm's law, we can rework those in these two familiar forms. So let's look at our first example, and here we finally get a payoff to something I said at the beginning of the video that might have been a little surprising. In the US, we're used to having 110 volts AC at the outlets in our walls. That can range anywhere from about 110 to about 120. But I said on the first slide that the peak voltage was 156. So what's that about? Well, it's because for all practical purposes, we talk about RMS quantities when we talk about electricity. So we want to think about the averages, in particular the average power output. So the 110 that you're told is actually an RMS value. Well, the RMS voltage is given by 1 over root 2 times the peak voltage. And that means the peak voltage is going to be root 2 times 110. And when I run the numbers on this, I get 156 volts. So if you were to look at the waveform of the voltage across the terminals of an outlet in your wall, you would see a sinusoidal function with a peak of 156 and then a low spot of negative 156, but the RMS average of that is going to be 110. In our second example, we're asked to compute the RMS current through a 100 watt light bulb connected to a 110 volt RMS power supply. Now it's key here that you realize the 100 watts I just told you is an average power. That's what we care about with light bulbs. We don't care about the instantaneous power. We want to know how much energy they use up on average. So this is an RMS value as well. I could call it PRMS, or I could do a P with a bar over the top of it to indicate the average. And so this isn't so bad. I just use P equals IV in the RMS sense, and I solve for the RMS current. And that gives me 0.909 amps, just keeping 3 sig figs here. Just for fun, we could compute the peak current through this light bulb. And so that would just be, if I go back to the definition of RMS current, the peak would just be square root of 2 times this number. So let's just write that down real quick. I naught would be root 2 times that, just to satisfy my curiosity. And that would be 1.29 amps. Okay, it's just a reminder that the peak current, as this resistor experiences an oscillating voltage, is always going to be bigger than this RMS average current. Finally, we want to compute the resistance of the light bulb in this last example. Well, we have the current, we have the voltage, so we could just use Ohm's law from that. You don't even have to convert those to peak values because I naught and V naught differ from I RMS and V RMS by exactly the same factor of √2. So I can say R is equal to V over I. Let me just be really specific here and say you could find the resistance from the peak voltage and the peak current. But if I divided the top and bottom by √2, then I would be talking about RMS values. So we can just be sort of flippant about it. And as long as we're doing everything in RMS, we just don't have to worry. And I get 110 volts RMS over 0.909 amps RMS. And I get 120 ohms for the resistance of the light bulb. Just to clarify what I was saying here, I could do the same thing with the peak voltage, which was 156, and the peak current, which was 1.29 amps. And I get the same 120 ohms for the resistance. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.